So the next step is image reconstruction by statistical image analysis. And of course, we need to we can obtain the response, but usually the refractive index change due to the charge carriers are usually very weak. So we utilize up-to-date image recovery algorithm to make the image very clear to obtain the refractive index change. So that's I'm going to introduce some of the method for this. So here's the things. Here is the original phase contrast image of TiO2, and what we can obtain for the time-resolved image as a raw data is something like this. So you can see many this kind of noises, and also some flickering of the light because we are using the pulse light as an illumination source. So from this, we cannot obtain the good estimation of physical parameters. So then we use several different image reconstruction techniques, and I'm going to briefly explain three of them. So one of them is, since we are using the pulse illumination, as I mentioned, pulse is very fluctuating for each pulse, and also inside the pulse light, there's inhomogeneous light intensity inside the beam itself. In this case, we use a flat field correction we used. And the other one is we observed many noise, interference noise, because this is illumination light is a laser, and laser usually gives a coherent or more of the noise, and then we found out the RPC, meaning the principal component analysis based algorithm could actually remove this kind of noise. And also we had a very small signal detection of the very small refractive index change. And in this case, lasso image recovery was very helpful. And lasso is a kind of enhancement of some specific feature in the data or image. And in our case, we can use a frequency, spatial frequency domain technique. So I'm going through step by step a little bit. So at first, flat field collection. Here's example images under the same experimental conditions. So meaning that these three images must be same. But as you can see, the brightness and also inhomogeneous light intensity inside the image you could recognize. Here is a histogram of the pixel intensity and the pixel count, and you could see even for these images should be same. The intensity was really fluctuating. So for to recover these images, well, we need to analyze. We have to flatten the backgrounds, and in the flat field collection, using the local mean filter was used, and then the background was standardized. So after using this flat field correction, we can obtain these three images almost the same. You could see that in the pixel histogram, these three has these all the data showed almost the same type of the histogram. Right? So we could compensate the field intensity and the inhomogeneity of the light intensity. And the next step is you could see this kind of ring pattern or noise, which cannot be avoided when you use the laser as an illumination of the light, which is called a Moore. And is due to the coherent noise, due to many kind of defects or dirt alongside the optics. You could observe this kind of noise. And actually, we found that RPCM method, which is a robust principal component analysis method in the image, we could recover it. I will just briefly mention here that in any image, there are several principal components, and meaning the low rank patterns inside the image in the vertical and horizontal directions. And we want to keep this major images smaller. And by using this L part and S part, meaning the sparse part, meaning the very rare events is separated. So by using this, the important thing is this kind of noise could be separated clearly, and then these more pattern was removed, and we can use this one. The third reconstruction technique is a lasso image reconstruction, because we know that in this image we have a periodical pattern, right? Because we utilize the stripe pattern of illumination, meaning that in this image we have some oscillating pattern, meaning in the frequency domain we have some specific frequency should be included in the image. So in the Fourier domain or wavelet domain, you have a sparse or some specific features should be enhanced. So by using this, this is a demonstration of the data and of the artificial data. So it's a very low SN ratio. So blue line is original, and then we added the noise signal. And after in the Fourier domain, you can see that some peaks in the spatial frequency domain. And then after the recovery, you could see that the red one is recovered and quite similar as the original response. So by using this sparsity recovery method, the original image could be recovered and enhance the signal. So noise removal and signal enhancements are possible. So by combination of these image recovery techniques, so from the original signal to recovered signal is something like this level. So you could now clearly see that the stripe pattern with a very high contrast ratio, right? So these kind of informatics techniques support the analysis.